Dear Acting Dean, dear committee, dear colleagues, family and friends. First, I would like to thank you all for showing up here today, and I would like to thank the committee for an interesting topic for the present trial lecture. The secondary data analysis, a brief overview. I will start the trial lecture by defining secondary data analysis, its background and advantages and disadvantages. I will define cause and effect and risk of bias in drawing a cause and effect, before I go on with how we may reduce the bias and how we may actively facilitate our ability of drawing causal inference through statistical methods. Finally, I will summarize the lecture and conclude. The term secondary data analysis was new to us, and I performed a literature search at the University Library and identified a series with 4 books named The Secondary Analysis of Survey Data. The term appears to have its roots in social sciences, but we have also used secondary data a lot within the medical science without explicitly calling it secondary data analysis. Secondary data analysis was defined in 1972 by the American sociologist Herbert Hyman as the extraction of knowledge on topics other than those which were the focus of the original surveys, or other types of data than surveys. So this means that secondary data analysis is a reuse of data material that primarily was collected for a different purpose. Usually, observational data are collected by a group of researchers with a particular aim in mind. A database is generated that may be used by other researchers who did not participate in the initial collection. These secondary researchers may have different fields of interest or different research questions than the initial ones. Additionally, or alternatively, the research focus may have shifted meanwhile the data were collected, and the initial researchers will perhaps aim to study a different research question than their planned ones. The founder of secondary data analysis is regarded to be Émile Durkheim, a French scientist living from 1858 till 1917. He did not reuse data in the sense as described in the definition, which was stated by Herbert Hyman about 70 years later, but he introduced more complex analytical methods such as multivariate analysis, which may be described as the study and interpretation of complex interrelationships among a multiplicity of characteristics. His book from 1897, Les Suicides, considering patterns of suicides across populations and nations in Europe, has become a classic as he was the first to front that societies function differently than the sum of the actions of individuals. Much of the empirical analysis in Les Suicides can be viewed as the progressive introduction of additional variables, and since this is an important characteristic of secondary data analysis, he can be regarded as the founder of it. However, the modern reuse of data, as we know it today, is not that old. Modern secondary data analysis dates from the 1950s and 1960s in the USA and Western Europe, when survey data archives began to be established, allowing for the utilization of the richness of data in sociology. Secondary data analysis, as we know it today, is therefore a product of the second half of the 20th century. It is becoming increasingly relevant since we continue to gather large amounts of data. It becomes easier and easier to collect data, since we are, for instance, all constantly walking around with a smartphone, measuring everything we do. Secondary data analysis may be performed on both qualitative data and observational data, or quantitative data, sorry. And I will describe that later. But first, the research process. In primary data analysis, you would first state the research question, and then collect your data in such a way that you were sure to answer your research question, and your statistical methods would be quite straightforward. In secondary data analysis, however, someone has already collected the data for you, and it is your task to formulate the research question based on what data are available and what is possible to investigate. Usually, this means getting to know your data before actually formulating the research question. Since the data were not collected for your purpose, the statistical analysis may be more challenging than what is the case in primary data analysis. I will now present an example of the research process within secondary data analysis. An example of secondary observational data is the Nord-Trøndelag health study, or known as the HUNT. HUNT is one of the largest health studies ever performed, and the material consists of survey data from at least 120,000 persons with 80,000 blood samples. Data are collected through 3 measurement times, forming an enormous databases, giving good opportunities for secondary data analysis. It is possible for research institutions to apply for the use of HUNT data against a fee. Once you have the data, you may look at what is possible to analyze. A second example is the secondary use of existing data from an intervention study. The secondary analyses were performed on 2 intervention groups that originally participated in a randomized controlled trial. One group received surgery with the disc prosthesis, and one group received a rehabilitation program. The researchers, or the secondary researchers, studied what factors could predict a better outcome in the 2 groups, and found that the factors differed depending on whether the disc prosthesis surgery or the rehabilitation program was received. So these are 2 examples of the secondary use of observational data and the secondary use of experimental data. The distinction between the 2 is important, and it may have a great impact on the content of a lecture under the given topic. So I will now present an overview of what the present lecture will contain, or what we will focus on. First, we may distinguish secondary data analysis into quantitative research and qualitative research. Quantitative research is the systematic empirical investigation of observable phenomena via statistical, mathematical, or computational techniques. It may further be divided into experimental designs and observational designs. Studies with an observational design may further be distinguished into studies with descriptive and predictive aims, and studies aiming to examine a cause and effect. The present presentation will only consider observational studies with the aim to study cause and effect, or with other words, draw causal inference. So I will now present a few advantages and disadvantages with using secondary observational data. From now on, this term will be abbreviated to SODA on the slides. Using secondary data that are collected for a different purpose than yours primarily has the obvious advantage of saving time and costs. Consider you want to investigate the association between obesity and hand osteoarthritis. You would need to find your participants, contact them, examine them, perhaps give them some kind of treatment or train them or something. And then you need to examine them again and perhaps plot your data. This would require a whole lot of your time and resources. But instead, you can find a data set that happened to include everything you needed for this analysis. These data may further be quite rich, and you could examine potential interrelationships and potential causal pathways between obesity and hand osteoarthritis. And further, you would have the possibility to test innovative methodological techniques, which potentially might shed new light on clinical questions. Secondary data analysis has some disadvantages. The most important one being that the data were not collected for the purpose of the analyst. This gives a particular challenge in establishing what is a cause and what is the effect in secondary observational data analysis. We are to a greater degree left with studying statistical associations. The reason we cannot establish cause and effect is due to the high risk of systematic errors in our design, called bias. The bias can also happen in the measurement and analysis phase. Such systematic errors may be called selection, confounding, or information bias. I will first define causal inference and each of these biases. Epidemiology textbooks are in fact not that good at describing causal inference with one sentence. They epidemiologists write several pages up and down with what causal inference is. I therefore summarized the most important characteristics. Causal inference is the process of drawing a conclusion about whether a cause gives an effect. So drastically simplified, to do so, we must be sure that the cause happened prior to the effect, and that the cause and effect cannot be a result of other factors. This is ensured in certain study designs where treatment groups are randomized to receive an intervention prior to observing whether an effect occurs. As an example, the gold standard for drawing causal inference is the randomized controlled trial as depicted. If we had all the time in the world and all the money we could dream for, this is the study we would like to perform. We would randomize a big population to either receiving diet and exercise or receiving their usual diet and activity pattern. And we could observe later whether the persons who were exercising got more or less hand away than the persons who were not exercising. However, if we don't randomize the treatment groups, we cannot be sure that the treatment actually caused the weight reduction, caused the hand away. Participants may just as well have lost or gained weight because of other reasons. And this particular problem with the lack of randomization is called confounding. Confounding is one of the 3 risks of biases and threats to our ability for drawing causal inference that may occur in our secondary observational data analysis. And we will now go through the different biases, which implies a threat to our ability for drawing causal inference. Bias can be defined as the incorrect assessment of the association between an exposure and an effect in the target population. It may be divided into the 3 main groups: confounding, selection bias, and information bias. However, in real life, several variants and overlapping between these concepts may occur. These biases lead to erroneous results from our statistical analysis and should always be detected and avoided, and always discussed in the scientific article. Confounding occurs when an extraneous variable causes both our outcome and the disease under study, and it happens mainly in observational research due to the lack of randomization to study groups. If you randomize participants to a treatment group and a placebo group, and you observe an effect, you should observe a similar effect if the participants had changed groups, meaning that the groups are exchangeable. Confounding means that the exposure groups are not exchangeable. Hence, we cannot switch groups and observe a similar effect. Instead, if you switch groups, you would observe a different effect, which is due to the confounding. For instance, the present example shows an observational study of obesity and hand osteoarthritis. From now on, abbreviated OA on the slides. We wish to study the causal effect of obesity on hand OA. We see by the directed arrows from a higher age to both obesity and hand OA that this association is explained by both the obese and the hand OA persons being at a higher age. With other words, this means that the obese people could not have switched places with the non-obese with the same effect, since the whole association is explained by a higher age. The groups are not exchangeable. A different kind of bias is selection bias. Selection bias means that the study sample selected is not representative of the population that is intended to be analyzed. This may be particularly harmful in secondary analysis, since we might want to study a different sample than what we have. The selection might be ideal for the initial purpose, but not for the secondary purpose. Selection may occur both in the initial selection phase and due to the loss of participants at follow-up measurements. It may also mean that some stick to a treatment program better than others, and the characteristic of the compliers might be different from the non-compliers. Likewise, confounding, selection bias may be drawn graphically, as here in a causal graph. Consider we have selected persons who report to have OA and choose to examine them and find out that they really have OA. We know that obesity is a risk factor for self-reported OA, but self-reported OA may also occur due to the other risk factors, such as genetic factors. The genetic factors and obesity have in reality nothing to do with each other. However, if we restrict the analysis to only those who have self-reported OA, we create a spurious inverse association between obesity and the genetic factors, which is not really there. Knowing that a person was selected into the study because of obesity tells us the same persons could not have been selected into the study because of genetic factors. The present causal graph therefore tells us that the obesity does not cause hand OA, since the selection of those with self-reported OA is a common effect of obesity and the other risk factors. This may be a bit tricky to get hold on, but we will come back to it later. In an ideal primary analysis, we would never design our study like this, since it obviously leads to a high risk of bias. However, this is what we get, and we need to take it as it is in the secondary analysis. A final bias which frequently may occur in secondary analysis is information bias, which is bias arising from measurement error. In primary analysis, we may choose on beforehand to measure the most important concepts in an optimal way, whereas in secondary analysis, we must take what we get. Consider, for instance, self-reported body weight. This guy sees himself as Superman and will report a body weight of 80, while he in reality is 120. When we divide participants into obese and non-obese in our studies, we use a certain cutoff, say 90 kilograms. This guy will be put in the wrong category, below instead of above 90, because of measurement error due to self-report, and our effect estimate for the normal weight may therefore be biased upwards. Likewise, our effect estimate for the obese group may be biased downwards. For instance, the effect estimate in which obesity was a risk factor of interest. For instance, in a study where obesity was our exposure. Sometimes the degree of misclassification will differ across groups. For instance, it might depend on whether a person has a certain disease, such as osteoarthritis. This will have a larger impact on our analysis and is called differential misclassification. In non-differential misclassification, the error is the same for everyone. In secondary analysis, we will be more frequently faced with worse extents of misclassification, since the data were not designed for our secondary purpose. So to summarize what we have discussed this far, we may divide primary data analysis into data that have been collected by randomization and intervention, and data that have been collected by observation. Once these data are collected, we may just as well perform some secondary analysis with a totally different research question than what we have in mind in the first place. The secondary data analysis may also be divided into randomization or intervention or observation. At what moment data are primary and at what moment they are secondary is not absolute. The transition phases between them will be changing. However, to be able to discuss the difference between the two, we need to make some rough divisions. Since the data under primary data analysis were collected for the purpose we wish to study, we can be quite sure we have found what we are looking for, and there are few biases. In the ideal world, we will be affected by no or only a few types of biases in primary data analysis. In secondary data analysis, however, we may have a greater risk of bias. The fact that the data were not collected for our purpose leads to higher risk of systematic errors in our analysis. It therefore makes it harder for us to say that the exposure or treatment we wish to study actually causes the disease. In secondary analysis, we are able to a greater extent studying statistical associations, whereas in primary data analysis, we are studying cause and effect. Since there are few risk of bias in primary data analysis, these analyses can be regarded to give us stronger evidence we have found a correct answer. However, it is quite time-consuming and costly to perform an entire new study. Perhaps you would have to wait for several years in order to observe an effect. So there is a trade-off between the strength of evidence we wish to accomplish by our study and the costs and time we have available. So to summarize this picture, we see that there is an ideal world where we have a little degree of confound or bias, and we have can be sure we have found a causal association, and we have a high strength of the evidence. On the other side of the scale, we have the observational secondary data analysis, where we are affected by a high risk of bias, and we have a lower strength of our evidence, and we are studying statistical associations. But this will be quite much cheaper. I will now mainly focus on the worst scenario with regard to our ability to draw causal inference, which is the secondary data analysis of observational data. Therefore, my goal throughout this lecture will be to shed light on to what extent we may draw causal inference from secondary observational data. This question is interesting since it would have a broad applicability and potentially save us quite a lot of resources. We will now look at a few examples of secondary observational data analysis and to what extent they are affected by bias. Although we have classified secondary observational data into one class with regard to risk of bias, there are some exceptions, and there will be different degrees as to whether the risks of bias apply. The Scandinavian countries actually have wonderful opportunities for performing very strong secondary data analysis on observational data. We posit several national registries in which biases may be heavily reduced by design. Registry-based studies allow for a large amount of secondary data analysis, as they may be coupled with other national registries. These studies will only to a very low extent be affected by selection bias and information bias due to the correct information that is gathered for most participants of the population. However, confounding may still be a serious risk of bias, since registry data do not include randomization to treatment, which significantly facilitates our ability for establishing a cause and effect. As an example, consider the National Arthroplasty Registry, which has a 95% coverage of all insertions of hip and knee prostheses nationally. The primary goal of the registry was the quality assurance of hip arthroplasty. It has afterwards been used to study risk factors, and as in the present example, the study of early post-operative mortality after insertions of hip and knee prostheses. Both death and prosthesis operations are quite certain variables that are not prone to misclassification. However, very few other observational studies have that few challenges with selection bias and information bias. So on the other side, I have an example of a study of body weight and osteoarthritis. The authors of this study performed secondary analysis of 134 matched case control pairs who were part of a study with the original aim to study estrogen replacement therapy and osteoarthritis. Participants were therefore selected for a different purpose than the secondary analysis researcher's purpose, which may introduce selection bias. In addition, the body weight information was collected secondarily by reviewing medical records. So the BMIs were collected at different time points for different participants, and we have no information on how certain the medical records were. The study indeed reported very high but quite imprecise association, and one should be very cautious when interpreting such results. The latter study with the high risk of bias is the rule rather than the exception. Not many observational study designs are as strong as the Scandinavian registries, and we are usually dealing with secondary data with a high risk of bias. So we have now stated that our main goal in secondary observational data is drawing causal inference, and we have looked at some examples of whether a typical registry-based study and a typical case control study may allow us to. In some examples, the risk of bias is evident and cannot be mistaken of. However, in many situations, they may be hard to detect and to act upon without having any tools for detecting them. Since doing secondary analysis will save us a lot of time and costs, we should look at possibilities that help us to identify and reduce the risk of bias, and accordingly improve our ability for causal inference. An important question in secondary observational data analysis is therefore whether we actively can reduce the risks of bias. With regard to selection bias and confounding, it may be possible through the use of causal graphs. With regard to information bias, it may seem harder. I will now go through the use of causal graphs and how this may reduce the risk of bias. Causal graphs may be particularly helpful in secondary observational data because the data were not collected according to our purpose. A causal graph is a drawing of our assumptions prior to the analysis, and it leaves the secondary analyst with greater analytic control. Causal graphs are relatively new tools within epidemiology. The technical details are the best described by Sander Greenland, Jamie Robbins, and Judea Pearl in several articles around the year 2000. The graphs are founded in mathematics and is an intuitive device for deducing the statistical associations implied by causal relations. They may require a little practice to master, since there are some basic rules that combined may seem complex. However, once mastered, they may facilitate many tasks, such as choosing variables to reduce confounding, as well as how to reduce selection bias. I will first give some examples of what may happen if we do not use causal graphs in our secondary observational data analysis, and I will then proceed with some rules and some more examples. We see here a causal graph in its simplest form, implying the assumption that obesity causes hand osteoarthritis. If we do not make use of causal graphs in secondary observational data analysis, we may easily fall into a trap by these two epidemiologists called the Table 2 fallacy. In scientific articles, the research findings are often presented in tables. Table 1 usually contains descriptives of the participants, such as their age, sex, education level, and so on. In Table 2, the first results are presented, which are the answers to the research question. In Table 2, we are therefore often interested in an unbiased estimate of causal effect of an exposure on a disease. However, many researchers are so afraid of bias that they put everything they can imagine into their statistical models to account for bias due to confounding. Such a headless adjustment for everything will typically rather increase bias, since we can happen to adjust for selection or intermediate variables. Hence, we may publish research findings that are wrong because of our desperate attempt to reduce the bias, in fact increased it. As an example, consider the following study of obesity and hand osteoarthritis. The researchers here has put almost everything measured into their model to adjust for confounding. Just to be sure, just in case, we see quality of life, diabetes, age, education, smoking, physical activity all being adjusted for. This is an attempt to make exposure groups similar to each other. However, instead of making exposure groups similar, we may end up unintentionally deleting causal paths, biasing our estimates towards the null. With other words, the researchers may have forgotten the selection bias and the possibility to unintentionally having adjusted for intermediates. So if we think further, we know that some variables are unrelated with the outcome and can be deleted. The remaining are interrelated in certain ways. If we take these interrelationships into account, we are likely to have adjusted for the variables that actually are confounders and should be adjusted for, and we are not that likely to have deleted interesting causal pathways. So by analyzing according to a causal graph theory and secondary observational data, we will be able to grasp the causal effect without falling into the fallacy trap. If we make proper use of causal graphs, we may not go into this trap, since we have reduced rather than increased risk of bias. A lot has been written on how to reduce bias using causal graphs. There are even free programs online available which allows you to draw your causal graphs and tell you afterwards what you should put into your statistical model. These are good tools, particularly when graphs become complex, since it can be hard to see, even for trained researchers or graph users, what to adjust for. All articles or programs developed, or written or developed, for aiding in reducing bias through causal graphs are based on some simple rules. I will briefly go through them, a few of them at least. Since this graph shows a biased non-causal association. Basically, this graph is biased since the obese persons are at a higher age than the non-obese, which is also the case for hand-OA, since the elderly tend to have more hand-OA than the young. If we adjust for the confounder, here depicted by a black box around the confounder, we make the exposure groups more similar to each other with regard to age. After having adjusted, we are closer to an unbiased causal association. Sometimes the variable lies along the causal pathway from obesity to hand-OA, as here diabetes. These are unbiased causal associations, and we know that if you are obese, you are likely to have more diabetes, which has been shown in some studies to be related to OA. Usually, you don't want to dilute such a potential causal pathway. Therefore, we can say you introduce bias if you adjust for a mediator along the causal pathway, although this will depend on your research question. So what to do if we have selection bias? This is an almost similar graph as presented previously when I talked about selection bias. The persons selected into the study are likely to be more obese and are likely to be selected into the study because of their obesity or other risk factors. However, knowing that the person was selected into the study because of obesity tells us that the person was not selected because of the presence of other risk factors. So we introduce a spurious inverse association between obesity and the other risk factors. Making the selection bias explicit in a causal graph like this makes it easier to see whether it is possible to get around it. Perhaps it is possible to adjust the selection criteria by design in order to avoid the selection of those with self-reported osteoarthritis. As an example, in a case control study, we might be able to manipulate the selection criteria for cases and controls such that having self-reported OA is not a requirement for selection anymore, at least for the controls. We are then to a greater extent studying the causal, unbiased association between obesity and hand OA. Secondary case control studies typically allow us as secondary researchers to choose our controls on our own. A second alternative is adjusting for all the other risk factors there are for self-reported OA. However, in an observational study, this is very hard since we may be faced with unmeasured confounding. For instance, genetic factors and early environmental factors are likely to cause our outcome. Being unaware of selection bias has led to spurious and weird associations having received way too much attention. This headline tells us that obesity may protect against a second heart attack, which sounds very unlogic. Without having their data material, we may just draw their causal graph to see what happened to these authors of the researcher article being the basis for this headline. This association is typically studied in a prospective cohort study, where subjects are followed up over time without receiving any intervention. In order to have a second heart attack, you must necessarily have a first heart attack. Otherwise, you cannot proceed to the second one. So all persons that are selected into the study are selected because they already had a heart attack, which they got because of one or more risk factors, for instance, obesity. In causal graph language, having a first heart attack, which is the selection criteria, is an intermediate variable along the causal pathway from obesity to experiencing a second heart attack. However, when we have restricted the analysis to only those with the first heart attack, there is nothing left over to associate with the second heart attack, because the heart attack patients perhaps are starting to exercise or set on medications, which lowers the risk for the second one. At the moment and in the future, we will perhaps be able to strongly... There is a possibility in the future that we are so well monitored and having everything measured that we do not even experience our first heart attack. And this leads us to whether it is possible to reduce information bias. Reducing information bias is harder than reducing selection bias and confounding. Up until now, secondary data analysis have often dealt with uncertain data, survey data. As an example, consider the International Physical Activity Questionnaire, in which you are instructed to report your physical activity level the last 7 days. Many have problems recalling their minutes spent being physically active and report an erroneous number of minutes, giving biased estimate in our analysis. In secondary analysis, there is not much we can do about information bias, since the data were already collected. However, at the moment and in the future, we are and will be able to strongly reduce the information bias in our secondary observational data analysis. Soon, we can have all our health variables measured accurately with devices that we are all constantly carrying around. So to summarize the last section, we have now described how we might reduce the risk of bias by using causal graphs. It is obvious that causal graphs may be an almost unavoidable tool for reducing bias in secondary observational data analysis. I will now go on by describing whether there are any ways we could not just reduce the risk of bias, but actively facilitate our ability for causal inference from secondary observational data analysis. So an important question in the secondary observational data analysis is how can we improve our abilities for causal inference from secondary observational data analysis using statistical methods? First, since you did not collect your secondary data yourselves, getting to know them is of major importance before proceeding to statistical modeling. You should get to know everything you can about selection procedures. You need to examine any missing observations and reasons for missing observations, and perhaps you should consider the use of doing something about it, for instance, multiple imputation. And you should then examine relevant distributions and frequencies of your variables of interest, and perhaps age and sex differences in these variables. After having familiarized well with your secondary data, you might take a decision of whether your data is of such a quality that performing the planned study will add to the existing knowledge on the topic, or whether you should consider performing a new data collection. This phase may be challenging and may be a trade-off, because, as most researchers say, garbage in gives garbage out, meaning that if you put the data or data with poor quality into a statistical model, you will have poor quality out in the other end. But what if that isn't true? Perhaps with the new statistical methods, it is possible to create something out of nothing. Secondary analysts believe in the possibility to create a good study out of data that may be not of optimal quality by the use of epidemiological tools for causal inference, and or by the use of statistical methodology, making the most out of and utilizing the available data to the maximum. Doing an attempt may be a step in developing innovative statistical techniques, which is necessary also for the clinical practice research to progress. The need for creativity in secondary analysis is explicitly emphasized in the sociology textbooks of secondary data. In order to do secondary data analysis, you need to be open to all new methods that may improve your ability for causal inference. One should be familiar with causal inference and the fundamental problem of causal inference, as well as the causal language, including causal graphs. There are some basic topics to start with. After having familiarized with our data and determined to go further with secondary observational data analysis, we can proceed to examine whether we could use any facilitators for causal inference and whether being creative in the statistical analysis phase might optimize our ability for causal inference at the moment or at a later time point. We actually have several tools for drawing causal inference that may be particularly useful in secondary data analysis. These may be combined or used together with more advanced statistical techniques. As an example, Hernan and Robbins describe how we may make use of inverse probability weighting for the facilitation of causal inference. Peter Rolstin has also described the propensity scores for causal inference, and articles have been written with the almost utopian title Instruments for Causal Inference, an Epidemiologist's Dream, which proposes it is able to adjust for unmeasured confounding. These methods may optimize our ability for drawing causal inference with the help of statistical methods. Inverse probability weighting may reduce selection bias. Propensity scores allow for a more efficient control of confounding, whereas the use of instrumental variables allows us to adjust for unmeasured confounding. However, it is important to bear in mind that in secondary observational data analysis, the use of these methods goes along with some unverifiable assumptions. Since we have not randomized to treatment groups, we are just replacing one set of unverifiable assumptions with another set of unverifiable assumptions. However, when we analyze our research question under different assumptions and observe a similar and robust effect estimate, we may be more certain we have obtained the average causal effect. Several statistical methods may be useful for optimizing the secondary data analysis. I have chosen to describe two highly flexible methods which allows for creativity and imagination. First, multi-level models, which are statistical models that vary at more than one level. Another word is hierarchical models. And second, structural equation analysis are a group of statistical methods designed to test a conceptual or theoretical model. I will now describe a few examples of how multi-level analysis and structural equation analysis may optimize the use of secondary data. Multi-level analysis may be useful in secondary observational data analysis, particularly for analyzing repeated measures or other clustered data. Repeated measures are called cluster data because they are dependent on other observations of the same construct and belong within a higher level, for instance, a person. So as an example, because you are at the same height your entire life, the body weight at one measurement time depends on your body weight at a later measurement time. The different body weight measurements at the different times belong to you as a person. We say that body weight is clustered within the person. This is an example of a study including repeated measures of body weight and hand weight. Multi-level modeling allows us to utilize more of the information that is stored within the existing data. For instance, the information lying in the dependency of observations. Hence, different methods within multi-level modeling helps us optimize our ability for causal inference using secondary observational data analysis. Structural equation analysis may as well be particularly useful in secondary observational data analysis, as it may function as a tool for analyzing complex causal graphs. It is a highly flexible statistical method that can investigate almost any defined model you like. Analysis using structural equations can vary from being strict confirmatory, testing whole models as hypotheses, or we may just use it for exploratory purposes. For instance, to explore whether a certain causal graph is more likely than another. This is an example of a path analysis that may be analyzed using structural equations. We could choose to examine whether it can be confirmed or whether other causal structures are more likely. For instance, perhaps the scenario of turning all the arrows the other way around fits reality better than this graph. A key characteristic of structural equation analysis is that the model is tested as a whole and either rejected or compared with other specified models. The individual parameter estimates are only studied subsequently after having decided on the model with the best model fit, which means that it suits the best with reality. The interpretation of the findings of structural equation models may require some training with more and more complex models. It should also be used cautiously, as it is sensitive to a low number of included subjects. To summarize this section, we can say that there exists methods for facilitating the secondary analyst's attempts at drawing causal inference. However, one must bear in mind that methods such as propensity scores and instrumental variables in fact just replace one set of unverifiable assumptions with another set of unverifiable assumptions. According to the secondary analysis textbooks written within sociology, it is stated that secondary observational data analysts require the researcher to be open-minded and use his imagination and creativity to make the most out of the data you have available. Flexible statistical methods to be used are, for instance, multi-leveling and structural equation modeling. So, short look into the future of secondary observational data. Our personal health data is to a greater degree collected by new technology out of our own interest and out of commercial interest. For instance, technology is being developed that continuously tracks variables such as blood pressure and glucose levels, and this technology may quite soon be built into smartphones, watches or contact lenses and so on. So the future's available data, perhaps without explicitly being a part of a study yet, have the potential to form enormous databases, giving unique new opportunities for epidemiology and public health. Consider only the potential of the total elimination of information and selection bias could have. Consider everything with regard to lifestyle is being measured correctly at everyone at all times. This elimination of bias would have a major impact on our abilities for drawing causal inference. However, although there is a large potential, we do not know whether researchers will be admitted to use the big data. Perhaps we are allowed to, but only in smaller samples due to privacy restrictions. There are many interests in personal data, and they have been called the new oil, whereas privacy might be the new green. Because of privacy and other ethical issues, we may therefore still be affected by selection bias, although the information bias is ruled out. If we as researchers do get admitted to analyzing big health data collected by new technology, we are perhaps also not sure how to handle it. We will have to develop new methodology for dealing with all the data, and this development will be very interesting to follow. So to summarize this trial lecture, we can say that the main goal of secondary observational data analysis is drawing causal inference, although secondary data are affected by a high risk of bias, including selection bias, confounding, and information bias. We should therefore attempt to reduce the risk of bias, which may be done by design, by explicitly stating our research or our assumptions that are based in theory and literature, in causal graphs, and then analyze them accordingly. In the statistical analysis of secondary observational data, it is particularly important to familiarize well with your data, since you did not collect them yourselves for your purpose. We should further consider the use of facilitators for causal inference, and finally, creativity and tailoring of the sometimes advanced statistical methods is required to make the most out of the available data. So to conclude, secondary data analysis will become increasingly important in the future. There is a large potential for time and cost saving by using secondary data analysis, and the only limit for our analysis and interpretation of it are our imagination, creativity, and available methodological tools. However, we can never overcome the fact that the data were not collected for the secondary researcher's purpose. Measures of effect found in secondary data analysis will therefore never be evidence for causal effects. The only thing we can do is presenting the assumptions that must hold for a causal effect to be valid. So the trial lecture was based on these references, and I would like to thank you all for showing up and listening to me.